Electromotive force. Electromotive force is frankly an uncomfortable name because it is not a force, it is actually a source of electric potential. It's measured in volts. The reason it's called electromotive force is basically historical reasons. And a lot of times now people just abbreviate it as EMF and they don't even talk about electromotive force. Now let's get to this battery here. I have a battery here in dashed lines. It is a source of voltage, and it also has an internal resistance because inside a battery you have metal, you have various processes that will cause voltage drops. So each battery has a source of electromotive force, or let's call it EMF, and a resistor. The EMF is the process that carries charge from low to high voltage. And basically what's happening there, a battery is full of chemicals, and it's taking chemical energy and turning it into electrical energy. It's turning it into a voltage. It's adding energy to every charge that comes through the battery. Now, the way to measure EMF, if you do not have the circuit connected, let's say you have a break here, I have a switch and it's open, no current is flowing. So if I'm going to measure, if I hook up a voltmeter to this point and to this point, and I have my voltmeter, there's no current, so there will be no voltage drop here. You're actually measuring the EMF, which is the maximum voltage that a battery will put out. Terminal voltage, and the symbol for that is capital V for voltage, sub T, is the voltage measured when a voltmeter is connected up across a battery's terminals. So here's the positive terminal of the battery, here's a negative, and if I take a voltmeter here and I hook it up to both ends, I'm measuring the terminal voltage. If there's no circuit attached, again, if I have a switch here that opens it up, the terminal voltage will equal the EMF. However, if you do have a circuit attached, look what's happening here. You'll have a current going through here. So if you measure the voltage here, it will be the voltage provided by the EMF, and you can see the E here, and it's going to decrease by the resistive loss in this resistor here, which is IR. So in that case, VT is equal to E minus IR. And if you don't have current flowing, well then terminal voltage is just equal to the EMF. From the previous slide, we found that the terminal voltage is EMF minus the current through the circuit times the little internal resistance here. You can see from the equation that the maximum terminal voltage will occur where there is zero current. In that case, this term would drop out and you would just be left with VT equals EMF, and I'll use the script form there. Now, to solve problems like this, consider this internal resistor here, which doesn't really exist as a resistor. It just models the resistance in the battery. It's in series with the EMF. So to find the equivalent resistance, we just add the internal resistance plus whatever the external resistance is.